Welcome to the third unit of work, energy, and circular motion. We're going to start off with the definition of centripetal force. This is an inward force that acts in the direction of acceleration that causes a change in the direction of velocity. Here's a diagram of, let's just say, a ball on a string. We're going to have a tension in the string, and we can call this the centripetal force. Our ball is going to travel in a circle. If we swing this ball that's attached to the string, it's going to have some velocity going around the circle. And it'll also have a centripetal acceleration in the same direction as the centripetal force. So this scenario is a ball on a string. And of course, this is not the only scenario out there. You could also think about fair rides where you're sitting and then you're going around in circles. Your centripetal force is going to be from the center of that ride to where you're sitting as you travel around in the circle. That's another example. Another example could be a car making a turn. That also has centripetal force, and we're going to do an example of that later on. But there are many examples of circular motion. But in this particular example, on a horizontal plane, your centripetal force, Fc, is the tension in the rope or in the string. That's in this case. We're not going to derive the formula for centripetal acceleration right here, and it is pretty complex. I'm just going to give you the formula right away for centripetal force, and then we're going to use that to manipulate it and find a way that we can calculate the centripetal acceleration. So the centripetal force is Fc is equal to m times v squared over r, where Fc is your centripetal force, m is your mass in kilograms, v is your velocity in meters per second, and r is your radius in meters. So we're going to go ahead and derive a formula for centripetal acceleration. The first thing we're going to do is find the velocity in the circle. And we know velocity is distance over time. In this case, we're calculating the distance around that circle, or in other words, that's called the circumference. We can calculate the circumference of a circle as 2 times pi times r. So velocity then can be defined as 2 pi r over t. The second thing we're going to do is square both sides of that equation we just found in 1. So that's v squared is equal to 4 pi squared r squared over t squared. We're going to use the fact that f is equal to 1 over t, which is frequencies equal to 1 over time in seconds. This is from grade 11 physics. And if we were to square both sides of that, we're going to get frequency squared is equal to 1 over time squared, which means that I can replace my t squared in the bottom of that equation to f squared, or frequency squared. So I am replacing 1 over t squared with frequency squared again. So that we can either use this one or this one. Our next step is to use our centripetal force equation from above. I'm going to replace Fc with m times AC because force is equal to mass times acceleration. I'm going to cancel mass on both sides, so we're left with AC is equal to v squared over r. Now I'm going to replace the v squared with what we found in part 2. V squared is 4 pi squared r squared, and one of our r's are going to cancel out. So we're left with 4 pi squared r over t squared. So this is one option to calculate our centripetal acceleration. The other option is using our other equation that we found in part 2. So AC could also be 4 pi squared r f squared, frequency squared. And this is another equation we can use to find centripetal acceleration. Now let's do an example. A car travels through a turn at 65 kilometers per hour. If the radius of the turn is 150 meters, what is the direction and magnitude of the frictional force needed to hold the car? And I'm going to give you an extra piece of information because it's not stated in here, but we can say the car is 1200 kilograms. So this car is held in position, and we want to find the coefficient of friction as well, denoted as mu k. Velocity was given to us in the question, but it's in the wrong units. It's in kilometers per hour, but we do need this in meters per second to use our equations. So I'm going to multiply this by 1,000 and divide it by 3,600. Which gives us 18 meters per second. Then we're going to find our centripetal force. According to our equation from above, this is m times v squared over a radius r. The mass of the car is 1,200 kilograms, our velocity is 18, and our radius is 115 meters. So our centripetal force then is 3,400 newtons. Now, because the car is held in position, let's think about all the different forces acting upon this car. So this car is traveling in a circular motion because it's making a turn. We have the centripetal force, and our force of friction opposes the motion. We also have our normal force and gravitational force to consider. I'm just going to draw them like this. So it could be drawn in more 3D-like, just because we're drawing in 2D, I'll just draw like that. So this is the diagram if the car is to hold this position. Because it's holding its position, it's not accelerating up or down. Otherwise, your car is either going to float in the air or go down to the center of the earth, and that of course is not occurring. So it doesn't have an up and down acceleration. It also doesn't have a left or right either. Because it's being held in position, it's not going to go more towards the left or more towards the right. So there is no left or right acceleration, which means that our centripetal force and our frictional force definitely need to have the same magnitude, so we don't have a left or right movement. But because the frictional force is opposing our motion, it's going to be negative for our direction. Or in other words, frictional force is minus Fc, which is negative 3,400 newtons. So that's one answer. The other thing we're going to do is find mu k. I'm just going to take what I have from here and replace frictional force with our formula for frictional force, which is mu k times Fn. We're solving for mu k. And Fn is mg, which is mass times acceleration due to gravity. This is going to give us 0.29. And remember, mu k is a coefficient, so it shouldn't have any direction. It should always just be a positive number. So our final answer is 0.29. In our last example, a rock is attached to the end of a 0.75 meter length of string. It is rotated vertically. If the rock has a mass of 55 grams and is rotated at a constant frequency of 2 hertz, what is the tension in the string at the bottom of the loop and at the top? Here's the diagram of what is happening. So this is when our rock is at the top of the loop, and this is when our rock is at the bottom of the loop. And so it's going to go in circles like this. The first thing we're going to do is find our velocity. And if we have a velocity, then we can find the centripetal force. Once we have that, then we can factor in gravity. Take a note that frequency, which was given to in the question, is in hertz. This can also be defined as 2 revolutions per second or 2 cycles per second. And that's from the definition of hertz. Our radius is 0.75 meters. We also need to find the circumference of the circle, which is our distance. Circumference can be found as 2 times pi times r, and our r in this case is 0.75 meters. So the circumference of a circle is 4.7 meters. From grade 11 physics, velocity can be found as lambda times f, where lambda is your distance for 1 cycle. And f is the frequency. So 1 cycle is going to be the circumference of the circle, which is 4.7 meters, multiplied by the frequency, which is 2 hertz. 2 times 4.7 is 9.4, and we are calculating velocity, so our units are in meters per second. Now we can find our centripetal force, which is m times v squared over r. Our mass is 0.055. V, we found that already, is 9.4, and our radius is 0.75. So our centripetal force is 6.5 newtons. Now we're going to analyze the scenario when our rock is at the top of the loop and then at the bottom. We're trying to find the tension of the string here. Here's our diagram. We have gravity acting upon this rock. We also have our tension of the string. And our centripetal acceleration goes in the same direction as our centripetal force, which is towards the center. So all three vectors are acting downwards. When you're thinking about the tension of the string, we want to think that the tension is pulling the string. To point towards the center. And then we want to think if FG is acting with the tension or against it. In this case, FG is acting with our tension because it's going downwards. Now let's try to write this into an equation. Our centripetal force are the sum of these forces, which is the tension of the string plus our force due to gravity. And we want to solve for tension, so I'm going to move FG to the other side. So FC minus FG will give us our tension. FC, we got that from above, is 6.5 newtons. FG, we can calculate that as mass times gravity. So overall, your tension is 5.9 newtons. So that is your tension if the rock is at the top of the loop, and then we're going to calculate again for the bottom. So here's your diagram for that scenario. FG is still acting downwards, but then your tension's a bit different. Remember, we're trying to go towards the center of our loop, which is our tension. And because it's going that direction, so is your centripetal acceleration. Now we're going to write this in terms of equation. So your centripetal force is going to be the sum of those forces, which is your tension minus Fg. Remember, minus to indicate that Fg is downward. I'm going to rearrange this and solve for tension, which is Fc plus Fg which is 6.5 plus mass times acceleration due to gravity, and this is 7 newtons. And that is your tension of the string if the rock is at the bottom.